Okay, so to start off, put your hands up if you're on the blue team or red team in this room. Keep your hands up if you have no idea what that acronym TiETW was just on the screen. Okay, great. So I'm here with a purpose. Amazing. So just a bit about me. I've been in the blue team for about 3.5 years. Generally do security, engineering, architecture, operations. My Twitter handle is there. I refuse to call it X. It's ridiculous. And I use arch links, unironically. So if you're horrified, you can leave. I think I want to preface this by any, maybe Windows sysinternal gods that might be in the room to please spare me. I am just a simple being, so we have bits of Windows internals being mentioned throughout this presentation. I am not the expert on it at all. So I'm going to make some sort of attempt at an agenda to sort of keep myself on track. And I'm going to start with a backstory because everyone loves backstories. It'll lay the sort of foundation of what we're talking about. We're going to analyze what data we actually get from our EDR. So in this case, it's going to be Microsoft Adventurez endpoint. Run over some simple scenarios for what I'm specifically looking at, go down the rabbit hole a bit, and then draw some conclusions, end the adventure for now. There's sort of the long title of what this presentation sort of actually is there, so you can sort of get an idea of what's going on. That may mean nothing to you, or it may have, just a jump of words, or it may mean something. And I'm going to promise now I'm going to aim for this not to be yet another EDR evasion detection talk where something insane goes on and nobody can, really, pull anything out of it who's sort of average on blue team and such. So, starting with a backstory, I had a red team occur against my organization in 2021. The EDR fell over predictably, and in effect, when we were doing incident response and doing the analysis, we determined that the malware would utilize process injection as part of its payload, and we could sort of see where it was going and sort of analyze that. And during this whole sort of process, and in hindsight, I started to wonder, would our EDR fall over if any attacker came and actually just used these techniques? And then I started to think, well, what data do we have actually, available to us in the first place? And just a quick primer on process injection for those who aren't aware. In effect, it's a way to get our evil into other processes running on a system. So the idea is we can use various techniques, which I will be discussing, that we can effectively use for kind of detection evasion to sort of hide where the origin of things are coming from. If a trusted process is doing weird things, it's much less likely to be detected. So, we want to avoid touching disk, we do all these other bits and kind of get our code into such a trusted process. So, sort of thinking about where we are in the attack sort of kill chain, is we're sort of within the execution, installation phases, so the attackers just got in, they're maybe poking about a bit, and they're maybe looking to do a few things, and expanding this out, and I've shamelessly stolen this from a kind of post on Purple Team from SpectreOps that uses this same sort of rainbow spectrum. I just really like the idea. We're sort of in this big spectrum, we're kind of zooming in onto process injection as a technique. So, we come from detecting a wide array of things to looking at something very specific. And within this, we'll have different commonalities of techniques that are used. Some will be more common, some will be less common, and some may not be picked up. So effectively, I sort of looked at this and I said, okay, well, with this specific technique, how deep can we go in actually investigating this? Can we develop sort of more accurate detections for this sort of behavior? And sort of taking all this into account, we have to really look at how does an EDR work anyway. So if you look at quote-unquote official documentation from EDR vendors, the picture you sort of gather is generally going to look sort of like this. It's understandable that EDR vendors do not want to publish their exact internals because attackers can go ahead and figure out how to evade them. But some EDRs will give you more, some won't. But this is sort of the picture that the EDR vendors want you to believe. In reality, this is more contextualized to Adventurez endpoint. We'll pull back various sources of information. A few we're going to talk about, so kernel callbacks, usual sort of user mode mechanisms. and also event tracing windows, which I'll also mention. This information is taken from Falcon Forces research from the MDE internal series, which I'm going to mention multiple times throughout this presentation. It is insanely useful if you use Defender, haven't looked at MDE internals, absolutely do. And we'll take all this data. The black magic component still says relatively black magic, but it's usually kind of, an AI if else infinite, statement, or we're using Yara signatures, or we're doing all sorts of funky things, data analysis to determine what is bad, and then we might get an alert, and we might get some, sample exploited events. In Defender's case, we do. So just going over a few of these, kernel callbacks pretty much provide a way for us within the kernel as a driver to subscribe to events that we might find interesting. So I've sort of categorized this into a few categories, but in a nutshell, when we talk about in the space of EDRs, the categories will be sort of when threads are created, when processes are created, when processes are accessed, and other bits. So I've kind of nicked a diagram from Forecore, sort of detailing this, which kind of puts it in a nice sort of visual view for us. There's also event tracing Windows, which is a pretty powerful debugging and application telemetry utility within Windows, and we get all sorts of information from it depending on the application running, what we're targeting. So in .NET applications, we have that feed in sort of directly to us, and we can see function calls, class names, and we can use this to sort of detect evil. So if we see a weird class name, sort of something weird going on, that kind of gets seen by our EDR, and we say that looks weird, we're going to fire detection on that. And we can introspect this a bit with some various open source tools. So Silk Event Tracing for Windows provides a capability for us to sort of dive into this. This is really useful for defenders if you're not using it. You can use it. It's got some built-in features to sort of stream to Kibana and a few other places, or Elastic. I'm not sure it has a KQL or Log Analytics stream plugin. So if you're a big Microsoft house out there, that's would be nice to see included. But we can, kind of get an idea of what's going on. So, and then additionally, we have function hooking. So when EDRs, when new processes launch, EDRs may tamper with the kind of call process that occurs within that process. So, in a nutshell, when we have a new process load, it'll load the libraries it needs to work. And we can tamper with those libraries to effectively redirect execution flow to the EDR, and we can introspect some bits of functions being called and what's going on to try to get an idea of, is it doing anything malicious? And then we have the Windows anti-malware scan interface, which will, in a similar mechanism, it acts as a library that applications can load to effectively pass information at runtime to the anti-malware provider to get scanned. So, from Net 4.8, this pretty much will scan all assemblies if we're using .NET. So, taking all this into account, we must be bulletproof. You have all these features, you see all this information inside these processes. The main problem with a lot of these techniques is they are all within the user land. So, if you're tampering with a process to get all this information, or the process, the things that write these events are based in the process can just control this and, kind of just circumvent them. So, with .NET Event Tracing Windows, if we have a .NET application, which is a popular, attacker tools and tradecraft, a lot of stuff is just written in .NET nowadays, or C#. If we have Event Tracing Windows enabled, the component that will write that information is based in one of the DLLs that gets loaded into our process. So we can just go ahead, tamper with that. The specific component was with the event write function in TDLL, which is a common sort of the lowest level in all processes before we get into the kernel space. We just make it return immediately or tamper with it in other ways. We pretty much do the same thing for AMSI with how AMSI DLL is loaded. We can just tamper with the scan buffer and do a few other things that effectively mean that data just either may get passed through, but it doesn't come back as saying this is malicious to the program, so stuff still executes. And you can kind of see this in most effectively components like PowerShell. You can, if you try to invoke Mimikatz through a download string or something like that, you'll get a block. But when you sort of patch AMSI, you can sort of just do whatever you want, and there's no sort of introspection there. And then if we're being hooked, we can just get unhooked. So if we know what the process looked like before the hooking took place, we can just overwrite the EDR hook to go to the function we want to go to. And then we can also, there's various sort of mechanisms so we can sort of employ here. We can sort of just get a fresh copy of NTDLL and then know what the original process information or the original sort of calls were like, and then just we're good. So great, we've just lost all of this really valuable telemetry. What do we have left to work with? Because we're going to presume that threat actors are patching this stuff out, messing with this stuff. The user land is a complete wasteland. It's pretty much Fallout 76. So it's the worst one. So we have kernel callbacks still, as obviously kernel callbacks occur within the kernel. So you can't tamper with that because it's not in user mode. And we also have the kernel mode event tracing from Windows providers. So any event tracing where that occurs, where the sort of thing to initialize that is within the kernel, it's not sort of, can't tamper with it in user mode, we still have that. So finally here enters this jumble of strings I had on the screen, TiETW, which stands for Microsoft Windows Threat Intelligence Event Tracing for Windows, which is a mouthful. The threat intelligence name is often a bit confusing if you don't know what it is. I've talked to an EDR vendors and bits sometimes, admittedly at a conference, so probably not the best idea to talk to the sales team, but they're not just not talking to me about their threat intelligence offerings. So it's threat intelligence of potentially abusable APIs used by application, not threat intelligence of how we usually think of it. And this pretty much operates at the kernel mode. So once we get into this kernel space, a call will be made to check if we are actually logging threat intelligence event tracing Windows. If we are, and the call is a call we want to check, we can go ahead and get that log. So this is obviously amazing for us as defenders because we have all this juicy data now about process behavior. So we can look at what we can get with ETW Explorer. You just pull this off GitHub and sort of dive into your local event tracing Windows diagnostics. And if we look at the threat intelligence component specifically, we can see all these features. These are generally going to be separated in sort of local, where the activity is occurring within the process, and the sort of underscore remote, I have a filter on there, which is where we're having remote API calls into other processes or from one process to another. We're generally interested in remote calls for identifying process injection. So with Microsoft Defender for Endpoint, one thing we have within Defender for Endpoint is we have the advanced hunting schema. So if you use MDE, you'll maybe know about this. This provides us with all sort of juicy telemetry and data we can use to roll our own alerts and kind of introspect sort of how bits of the operating system are working, and it provides really useful data. So we get different sort of tables, and TiETW events are actually passed into the device events table. So we can take a look and see what we get and perform a bit of a mapping. So generally, we get the sort of alloc virtual memory remote API call. We get map view, queue user APC, and set thread context. A bit more detail into sort of how these bits work are kind of coming up. But that's a good range for sort of things that may occur. So we can also see a few others in here. Usefulness is debatable, but the remote calls are stuff we're mainly interested in. And we can also just take a look at what we're missing. So we're missing, at least from the events we have in device events, changes to remote memory protection that will occur during these sort of process injection potentially. Memory reads, memory writes. There is an event for memory writes to LSAS, but nothing else is logged, so that's under a different name. It used to actually be called write VM remote, but Microsoft changed it because it was kind of confusing, so that's now write to LSAS process memory. A few other components that can be used for process hollowing, which is pretty much where you spawn a new process, carve its guts out and shove your evil in there, and then get it to run your evil. And then we're missing two for the thread hijacking component, although set thread context we do have, which is used in-thread hijacking. So we at least have one of those, and that's usually good enough. And we can also look at the Defender for Endpoint timeline, which is pretty much a feature within Defender for Endpoint where you can look at a timeline of all sort of events going on with your, with a device. And there will be generally more data there than there is in the device events tables or the advanced hunting tables. And we get some other interesting calls and bits here. Also, some bits are missing, keenly, memory, remote protect, and remote suspend thread. So we can potentially think about how to pull that out. And overall, I think we just want to kind of stop a second and say, okay, what should we be paying attention to? So we can split these API calls into sort of mechanisms to get your memory, get your evil code into a process, and ways we can then go ahead and execute it. So map view is a way to sort of map a sort of shared section of memory from one process to another. You can use it to reflect code in a remote process. And then virtual allocators, sort of when you want to allocate a new memory region within a process. So when we sort of shove our evil into your processes, we can call either two of these methods. And then for execution, we can potentially use thread context if you want to get an existing process and hijack what it's doing. We can create a thread. Create thread being a kernel callback, so not TiETW, but provides us with some mechanism to monitor things going on. And then there's also an asynchronous thread that just waits for the process to become, or the threads to become like alertable to see what's going on and then execute that context. And more would be nice, but we've generally got plenty to work with now. So, we have all this lovely data. What could possibly go wrong? And when you sort of dig into this more, you realize, the threat intelligence Adventurez Windows provider is protected by anti-malware process light protection, or requires a process to have a protection level in its access control lists of anti-malware light. So in a nutshell, when it comes to process protection levels, effectively within the sort of user space within Windows, processes can have different protection levels that will kind of implement access controls on if you want to, dump memory from, let's say Defender. You can't do that because you do not have the sufficient rights as even system running PowerShell to talk to or kind of hook into Defender's logic, because they're protected with a different protection level. So, this is generally very annoying. And in order to access this data, we need a early launch anti-malware kind of driver with a kind of corresponding signature. And we have to submit our stuff off to Microsoft for validation with their hardware quality labs and do all this stuff. But essentially, as a poor blue teamer, we're not getting access to this information, at least directly, without doing some shenanigans. We're not an EDR vendor. So, with all of this, you think maybe Microsoft and Nav have an excellent reason for, not letting standard processors get access to information. Maybe there's some explanation. Well, I didn't really reach out to Microsoft directly to sort of get information on this. I took a quote from a blog that contains some really useful information on how the threat intelligence for Windows kind of works within the kernel. But as it's a quote because as I'm not saying this, hopefully Microsoft can't do me for defamation. But it's extremely odd how they would limit this to sort of a proprietary sort of co-op program, make it all restricted, not publish any information about bits, and it's also their operating system. Microsoft really have billions, but not going to say any more on that. But okay, so if we don't have direct access, that's fine. We can analyze what info we do get. So when we get these events through, Defender's going to generally give us the initiating process and the target process information. And we don't always get the extended information that the raw event tracing Windows threat intelligence gives us. Sometimes we don't need this. Sometimes we kind of do need it. It's kind of depends on what you're working with. And that's also, subject to context. Defender's not always reliable in actually giving us information. So looking at some of the events in the threat intelligence Adventurez schema and mapping it to Defender, we generally have calling process information, create times and target information, and then depending on what we're working with, we might have different parameters. So changing of remote memory protection will contain information on the type of protection that's changed, whether it's read write, read execute, what address it occurred at. When we map this over to Defender, we don't usually get these extended details, but what Defender will do is it will use the process start key feature within this log to map these events to process start information, and then we can sort of figure out, okay, what process is this? What was its process file name and what was its path? So we get sort of this juicy information. When we're actually dealing with these events though, not having the calling process start key or the process start key information is really annoying for doing correlation. If we ever want to marry two events up, not having process start key can get very annoying. So I'm not sure why they don't pass it through. Apparently we're not qualified to be having the process start key given to us. But so that's just general analysis of that schema. So we think we have all this juicy data, we have all this lovely content we can use. Surely everyone who uses Microsoft for Endpoint is using this stuff. And when I originally was sort of looking at this in 2021, it was pretty barren. It's a bit better now, but if you kind of look for references on the internet of some of these things specifically, the amount of documentation is near non-existent. Generally less than 10 results with sort of Google search. It's pretty abysmal. Currently we have Falcon Force and SpectreOps leading the way on the research and components for this. And the Falcon Force MDE internal series, amazing, as I already mentioned, read the MDE internal series. And kind of analysing some of Falcon Force's alerts, we can see that we kind of, a lot of what Falcon Force have developed is about using a feature within Defender Advanced Hunting where we use the file profile function, look for remote in calls coming from processes we haven't seen before, or is unseen to Defender, or the signature is unseen to Defender sort of globally, and then we raise an alert. And these alerts are often quite low effort and very very good results, low false positives. So we can run that, ship up the stream, and sort of job done. But I'm just wondering, sort of outside of these parameters, there may be things that go on, which means you're not executing from a random dodgy process. Maybe you're already inside somewhere through whatever means. Maybe you're using DLL search order hijacking to get into processes. So this may not always be the case. So how can we look at this and do our own detections outside of these components? So you think that MDE should detect all this stuff perfectly because we have all this juicy data. And the reality of that is it just doesn't. So it's going to be for a variety of reasons, mainly sort of global customer tuning. You don't want a billion alerts firing out. So, sometimes it just misses things. And we could either find that out through debugging. I'm not doing that. That's insane. Or we can just mess around and find out, play with Defender, do our own sort of purple teaming and figure these bits out. So going back to the process injection techniques I talked about, among them we can have many different sort of combinations, variations. So let's dive into some of these combinations. And first we sort of have kind of classical effective where we just create a remote thread. So we allocate a virtual memory space, we write to that memory variable code, create a remote thread where variable code is in that process, job done. And then we have using map view with a thread hijack, which is a lot more convoluted, but achieves the same result. Process does our evil deeds. So we're going to use a combination of testing tools to do this. Firstly, we want some tools that will give us information on what the threat intelligence for Event Windows provider is doing, because we'd like to compare it with Defender and see what we could get in an ideal scenario. And we're also going to look at process injection tooling, because obviously we need to test some of this stuff. We're going to need to use some tooling to actually simulate these activities. And the first stop on this sort of train is going to be the TiETW agents. So this is a sort of open source tool that sort of emulates how EDRs might behave, and will look at and watch some of these events. And you can sort of develop like Yara signatures, rules, look at the sort of process memory that's getting written. It's just a nice sort of base and a nice sort of project. And we're going to assign this with a different project, or use it with this project called PPL Runner. And in a nutshell, we can assign our own drivers, put Windows into test mode so it lets us do what we want, and then get this running on anti-malware process light so we can start doing some of this investigation and debugging. And then for our injection tools, generally this is going to be pull stuff off the internet, make sure it works, job done. I think one to mention is Sharpen Hooker. It's just universally works amazingly for net applications to patch TiETW and AMSI all in one go and do unhooking. So quite nice. And we can validate this evasion and just have AV real-time on. We go from events being logged in TiETW to no events being logged. And we go from AMSI blocking our application from running to AMSI not blocking our application from running. So great, we've sort of emulated all those user mode bypasses that we know are subject to just kind of shenanigans. So first test, let's go with sort of this classical create remote thread mechanism. And we go ahead, run it, and cow pops. And Defender sees this, and we get an alert, so fair enough. Moving on to map view and set thread context. We give that a go. We see TiETW has seen a map view remote and also a set thread context remote. We get that action type into our events. Then we go and look at Defender. It sees it, we just don't get an alert. So the only reason I can sort of fathom, again, the black magic and optimization tuning has just decided it's not going to alert on that. This is not good for us for not being able to just detect this blatantly obvious process injection. But we can see the events. Interesting enough, Defender will flag this as a cyber data true or a one cyber event, which aggregates a bunch of stuff that, in a nutshell, Defender finds interesting. So let's just do it ourselves. So we see set thread context from our API call. We're going to join the map view section occurring, and we're pretty much just able to determine that pretty easily. And then we have alert, and we can go further with that if we want to perform some extra optimizations depending on the fidelity and your own environment. So we can just also join information on network events. If a remote thread is created or some activity like this happens, and immediately get a network event, it's generally indicative that as an attacker we're moving about trying to get our kind of calls and command and control structure into other processes. So if this happens and then we immediately get a network callback, that's weird. So we can alert on that, and also Sysmon has event ID 3 for network connections. So depending on what you're using, you can maybe sort of translate this logic to your own EDR environment depending on if it gives you this information. And then I do want to have a point on when we're doing call mapping with two or more calls and we're trying to correlate events, because we don't have the calling process start key, it's a bit chaotic. We can pretty much pick a mix of process ID information, target information, initiating information, device, and then do time correlation. And if we do all that, we generally get a pretty reliable detection. But it is easier than sort of doing this when we have map view. So in my environment, I have about 800 endpoints. The only thing that actually uses map view is Firefox and its own child processes. I don't know what's going on there, but I just sort of assumed, okay, if a map view call happens to a process, from a process, and the image path is both the same, we don't care. And on the past 7 days in my environment, I get nothing. In the past 30 days, I get 3 alerts. So pretty much for any red teamers that might be using MapView out there, it's really easy to detect. Depending on your environment, your mileage may vary, but for what Defender doesn't detect, we can just detect that pretty easily. And I went, okay, let's kind of up the scales a bit. What about some other scenarios? So we detected set thread context with MapView being rare, but let's change to allocate virtual memory remote, which is a lot more common. We're also going to look at just not playing with threads at all, so kind of threadless, and also asynchronous queues. Asynchronous queues is actually, even Defender detected it was actually very easy. And I also want to introduce a new category here called sort of the Defender++ category that I'm calling it. But in a nutshell, we're just sort of pulling information from the timeline to enrich our alerting. So what Defender doesn't give us, we can just try and grab out. And we're going to change tools here so to kind of scale up a bit more. So there's a utility called TiETW for TiETW research that is really useful. And I've switched to it because it's lets us kind of stream processes in a way that's and get events that's just more efficient. And I think also considering what we're doing, having to re-sign every time we reboot and do all this stuff with Windows test mode it's just annoying. It makes testing more difficult. So can we just not use it? And it turns out we can in a way. So fun fact, for about 3 years there was a exploit within Windows that basically bypassed process protection entirely, and Microsoft took ages to fix it. And born out of this, the author of TiETW actually developed a fork where they would use this exploit to elevate their own process to anti-malware protection light to get this data. So, obviously that's patched now, so we can't really do that anymore, but we could have done that on our production environments. Do you want to use an exploit to get data that may let you do detection engineering better? It's a grey area. But, so that's no longer a thing anymore. But we do have the ability to also use vulnerable kernel drivers. So we have a utility that exists called the kernel driver utility. Really, it should be called the kernel driver abuse utility. But the author of TiETW made a pull request into this component to add a feature to elevate to anti-malware process protection light. And when we compile this and run this, Defender doesn't actually care about it. It does seem to pick it up if you have potentially unwanted application detections on, but you don't get detection when you're using this, which is a bit weird. It doesn't work if you have hypervisor code integrity on and you're using core isolation, but elsewise generally seems to be fine. And when we sort of kind of get this and map this process information, when we have this data, we can pretty much take these process start keys and sort of build our own pretty much process analyzer to see what's existing, and then just do the image joinery ourselves. So we have all the information and we have the capability now to pull these threat intelligence eventuating Windows events without having to use test mode, and we can just use an exploit and do what we want to pretty much run that and get it into process protection light so we can start processing this data. Probably still not a good idea to do in production though, for reasons. If you don't have hypervisor code integrity on, you could do it, but if you don't have that, you probably have bigger problems. So, with all this data, all we have to do is just sort of manually map what the process information is, and then write a bunch of horrible PowerShell features and bits, and we can get the threat intelligence data into our log analytics workspaces and have something sensible to work with, and then join that information and enrich it as we need. And then considering the sort of other category I introduced, which was the sort of Defender++ category, how are we getting that data? So it turns out within the Defender timeline, when you sort of look at that, you can kind of introspect the network, what's going on there. It's going through an API proxy, but there's this component that will tell you the source URL or source URI that it comes from. And effectively comes from what effectively is the sort of production Defender for Endpoint sort of service API. So we can just make direct calls to that and get information back. So you can sort of kind of pull that timeline information in and get, what we care about. Now, doing this is a bit dubious. There's no real explicit guidelines around using this, and we can try to stick to some established components, but it's really just kind of me making up new limits. So if you want to pull all 7 event types we're interested in, we could do 480 devices over sliding scale. It's more kind of use at your own risk, really. and we can optimize what data we pull back from this and sort of, do this in a bit quicker of a sense. So we can use the search field to look for some of these events and these kind of protections that we sort of care about. And we can also use Defender Harvester. So you don't need to use or write your own terrible, monstrous PowerShell scripts or whatever to pull things back. Recently in October, a new MD internals came out where the Falcon Force actually released a tool that we could just use to do this. So very useful. Use Defender, check it out, contribute to it. Very nice. And then we need to sort of decide what to pick. So I just went for memory protection and resume thread events. And okay, so we now have a way of correlating this raw data. Practically, we never use it in production environment. It's useful to see sort of what's going on. And we have our Defender++ data grab that we can sort of aggregate with bits. So now let's give this a test. So with the virtual exec for context, we have both these events. We'd assume that there'd be absolutely no problems. It should be a breeze getting all this information. And okay, fine. Let's take some statistics. So virtual memory remote, very common. For context, less common. So kind of progressing with that. Let's go run the simulation. Look what's going on. We see that Defender seems to not be able to map the initiating process information for what's going on. So that's weird. But we still get like another event that's quite useful that we could potentially sample out. And then we take a look at the set for context call and realize it's just not reporting process ID initiating information at all. And when we look at the actual raw API, we see it's just not there, which makes mapping it a nightmare. And we look at the threat intelligence, for interesting windows, do a bit of sanity check, everything's there, it's fine. So, okay, let's try to do time correlation. So we know what was targeted, we just don't know what did it. So when we join these events, we can sort of try to do time correlation. That usually would work. Any caveats is that when these events are shoved into our logs, the set for context seems to just all be lumped together. And we don't have the timestamp initiating information. So we can't really kind of do time correlation effectively. We're doing about a 30-minute span, but not within 5 seconds. And I was interested about kind of looking into this, so I kind of also did a few other bits, and I noticed that the NT allocate virtual memory was also delivered 10 minutes late exactly each time. I tested this across a production environment, test environment. Both seem to have similar results, so you can maybe do some magic on trying to analyze what this difference is and then pull it back to what it should be, but it's sort of in the air. So we can go again on this, expand the time correlations to 30 minutes. What we can do as well with this is pretty much use the sort of past 14-day trick, which if you use Sentinel, you're probably tired of using this. Microsoft Sentinel's max look back is 14 days. So in effect, we'll look at the current hour, we'll look at the past 14 days, we'll get rid of everything for the past 14 days, and we'll look for just where this happens newly and in kind of places we haven't observed it before. And we do that, and we implement a detection, and we get a result. So we're able to sort of detect that. Mileage may vary, but we managed to pull it off. Then looking at thread suspend, I did look at this, waited a few hours. I didn't get anything. So I don't know what happened there, but there's apparently a lie. And running a bit of a sanity check on this sort of initiating process information, I thought, well, what if the device events are just being outrun? So, or the actual, it's running too fast for Defender to do something about it. And I, waited ages and still nothing. So when this does happen, there's a chance with Defender, either the initiating process information will just be not existent in this call, or there'll be no process information at all. You just have process IDs, which sucks. Makes correlating these events just awful. So I went ahead, looked at some statistics, some bits. How reliable is Defender's statistics? Generally, we had some instances where we have no initiating info, where we'd have no info at all. It's generally reliable with everything but set thread context remote API call, which just had nothing anywhere. And I also included create remote thread API call, which is kernel callback. So just to see the difference. So they should be using a different system, but it's still not reliable. So I don't know what's going on there. Maybe it's a Tuesday and rainy, and that's why defenders just decided not to give us that information. I don't see any reason why it won't give us the information. We have it. So beats me on why that exactly is occurring. The using threat intelligence Adventurez in Windows, the result is yes. Yes, we are able to run a monstrous query to join all this information together and get an exact result. So, then one other technique I want to mention is kind of using threadless. So we've looked at things that manipulate thread context and creation of threads, but what about just allocating virtual memory? So at B-Sides Cumry 2023, there was a talk called Threadless Inject by Seri Coburn, and this is pretty much a method to sort of tamper with the memory processes in order to kind of hook components and kind of inject code and get it to run things in a way that just don't involve thread creations. So, not really explaining it here, you can go watch the talk, and I went to go get it running. Seems that someone at Microsoft saw the talk and wrote a detection for it. And all I had to do to bypass that was add a no operation in the middle of the shell code it used. And there was no behavioral signatures, so I'm good to go. If we're just using raw Defender events, this is just part of detect, excluding profile for unknown apps. You get one virtual memory from an API call. Not really practical. If we're using sort of the Defender++ bits, we'll notice that the process information and initiating process information are flipped for some reason. We can sort of work with that, but it's a bit annoying. But Defender does see this, and I ran this about 710 devices. Had about 14k of these events occur in the last 24 hours. Shoved it into log analytics for our own sanity, and then we can sort of start working with that data. So, looking at the components, we can see, maybe we could write some detections based on the region size, but, this could be changed by attackers. Some bits with how this sort of works is, at the moment, the memory protection regions will fluctuate, so you kind of get this sort of pattern occurring. So, we actually profile that. But what you also can do is just join this information with the, a few other components. Memory protect with allocate within a relative time, do some time correlation, and I managed to actually get a working alert out of that. That wasn't too prolific, but your mileage is going to vary quite heavily on that. And looking at Adventurez in Windows, we have additionally the memory protection sort of kind of change that occurs. We don't get that from Defender, but that's also pretty useful. And just a quick detour. We do actually have local memory protection events in an action type, but we don't have any information on what the protection change was. So there's a utility called TiETW fluctuation monitor that's been at a Black Hat talk, and the idea behind that is if you mark a code page as read write execute, it shouldn't be changed back. So if Microsoft actually gave us information on the change of the memory protection, we'll be able to sort of implement this ourselves and look for potential sort of malware inside the process, but we just don't get that. But just wanted to detour because on the topic of memory protection, it's generally interesting. Q user APC is ridiculously easy to catch. Defender caught it within 30 minutes. We actually got an alert. That's great. And looking at our own environment, in the past 90 days, I did not see that API call anywhere, which is pretty prolific, so, or pretty significant. So we can just go ahead, write alert, see that, probably evil. And then just want a quick mention for the Falcon Force rule sets. So looking at virtual memory allocations from unknown processes is generally very reliable, low fidelity. Past 30 days, I have 10 results. We can go ahead and use that, but we want to consider whether we probably shouldn't be letting these unknown processes run in the first place. So, we can sort of block that with Defender attack surface reduction rules. But just a sort of bit of a detour looking at Defender or sort of Falcon Forces components there. And, we can sort of dive into sort of the black magic occurring within Defender here. So, within the create remote thread, I thought, well, what if we just do nothing for 10 minutes and I added it in, no alerts. So if you're in doubt, if you're on the red team, just wait 10 minutes before you issue a remote thread creation. It should just escape the sort of logic that Defender has set up for detecting this stuff. Easy. So So obviously I've talked about kind of a lot. I want to make it generally fair. EDR vendors need to strike a balance between noise and detections. Fair enough that some stuff isn't detected, and more event processing is higher cost. It sort of pushes people out of the market, prices go up. But in fairness, for some things, it would just be nice to see these raw events because when you sort of put this in the hands of the SOC, you're going to get better sort of alerting and detection, more fine-tuned components. Practicality of using some of these bits, hammering the MDE service API is probably not a good idea, but you could sort of target effectively. Mainly during incident response. If you're doing incident response, a few devices, pull all the information, get it into log analytics. Boom, you've got something you can actually process in a sane way that's not going to drive you mad. If you're doing incident response with MDE scrolling through the timeline, you actually want to throw yourself out the window. It's horrible. And production, we're most not likely going to use kernel exploits to get TiETW. It's a bit probably not a good idea as a defender to be breaking your own systems. But monitoring our own processes, we can sort of get rid of the chaos here. So overall, if there's anything to sort of take away as things we should aspire to influence on EDR vendors, Microsoft, etc., if we had access to this information, we could do all sorts of wild solutions where we could, potentially write component scripts, bits on endpoints to sort of inspect what's going on, see these components, and do all this crazy stuff that will let us sort of go into what's getting written, memory bits, and we can sort of do a lot of cool stuff. And why shouldn't EDR solutions be allowed to, let you get some of this data? So, unless the big bad wolf says no, but I'm not sure about that. Overall, to be continued, we could, use potential ideas. So within Sentinel, we have Jupyter notebooks. We could do some AI, ML, buzzwordy stuff, analyze all these various calls, come up with something that, implements some detections with these. We could, if you're using Microsoft, if you know the stack, hook to logic apps that do weird and wonderful things, don't process memory, take screenshots, do all these wonderful components via kind of open source tooling we can use for incident response, kind of really thinking on the sort of SOAR mindset. And really concluding, it would be nice if Microsoft could pretty please give us access to the data. They probably won't, but we can annoy them. If your SOC can't hack the planet, how are they going to defend it? So, if you have SOC, you can sort of time the allocation to sort of, I wouldn't say reverse engineer their EDR tools because that's definitely against the terms and conditions, but inspect how they work, find out these components, understand telemetry and events. And if you're a red teamer, avoid map view and APCQ, opt for threadless because it's very hard to detect. And really the TiETW is not actually that scary because no one seems to use it properly, or at least Defender doesn't. And finally, at my end of my ramblings, so that's all I had. I don't believe we have time for questions.
Yeah, I believe we've run a little bit over, but yeah, no, give a big hand to Luke.